Welcome my friends, welcome to my next lecture. Now this lecture my plan is to talk about what is called equipotential curves. So if you remember I talked about vector fields, okay. Then there are three ways you can visualize it. One of them is that arrows, via arrows, then via integral curves, and then the last one is that equipotential curve. So that's I will start with that one. What is equipotential curves and how you visualize your vector field, and then I will start with what is called notions of curl and Laplacians. Of course, I think I need one more lecture to complete it, but let me just start with equipotential curves to visualize my vector field. Okay, so as I said, so I think I should start with the visualization of my vector fields via equipotential curves. So okay, that's the heading I have written, that equipotential curves method to visualize vector fields. So that means if I have a vector field, then how I can visualize. Before that you have to know what do I mean by equipotential curves, right? So look, so assume that capital F is a gradient vector field. So that means I am starting with a vector field, a special kind of vector field, which is gradient vector field, and you know what is gradient vector field. A vector field capital F is called gradient vector field if there exists a what is called scalar potential or scalar field such that I can write my capital F as the grad of small f. If that is the case, then I will say that my capital F is a gradient vector field. Okay. So I am starting with a gradient vector field. Now to visualize the vector field capital F, draw the level curves. Now level curves you know, right? So that's what I am saying, to draw the level curves of the scalar potential. So therefore capital F is a gradient vector field. So therefore I can write capital F as grad of small f, where small f is a scalar potential. That means it's a map from some domain subset of Rn to R. And you know if I have a kind of that scalar field or scalar potential, then you know what is the integral level curves for that, right? Of course, in for R2 to R3, I have discussed if I have a functions from f like some domain subset of R2 to R, or some functions f some domain subset of R3 to R. So those level curves you know, okay. So therefore I am assuming that okay, I have a gradient. Again, look, I actually am starting with a vector field capital F. That means it's a function of two variables. That means I am actually in R2 setting. Okay. So therefore I have a capital F is a gradient vector field. That means I have a scalar potential or scalar field. Therefore capital F is exactly equal to gradient of small f. Okay. And you know what is the corresponding notions of level curves that I have already discussed in my last couple of lectures. Not last couple, I think 1 week before I have discussed that what is the, in fact in the beginning I have discussed that what is the level curves corresponding to the scalar potentials. Okay. So then you can have the notions of what is called equipotential curves. Okay. So what I have, so to visualize the vector field, draw a level curves of the scalar potential small f corresponding to the vector field capital F. Okay. So for example, I am starting with an example, like if I consider this vector field capital F, which is flipping, that means xy goes to y comma x, right? Of course, this is a gradient vector field, and what is the function? So this is the corresponding scalar potential. I already discussed in my last couple of slides that if f of a small f at the point xy is x times y, and this is the corresponding scalar potential, that means I can have this capital F, you can write it as gradient of small f. Okay. So this is the scalar potential. So now what you have to do? So draw the level curves of this scalar potential. That means I have to draw level curves of this potential. Okay. Now if I draw a level curve, what is the notions of level curves? I already discussed. So it turns out that the corresponding curves is xy times c. That means what? That means you have the rectangular hyperbola. Okay. So xy times c is, that means the rectangular hyperbola, and they are the corresponding equipotential curves of f. Okay. So what is equipotential curve of f? If I say it one line, start with a gradient vector field, that means this capital F corresponds to a scalar potential small f, and get the level curves of this scalar potential that will be same as what is called equipotential curves of capital F. Now if I draw it, for example, this is the, like in terms of arrow, you can have the visualization of my vector field, this capital F, okay, in terms of arrows. And what is the corresponding equipotential curve? So this is the what is called xy times c, that means it's a rectangular hyperbola. So that means this is the one, right? This is the one, depends on c. Okay. So now of course you know that I can visualize my vector field in terms of integral curves as well. And if you remember, corresponding to this vector field, you actually have calculated what is the corresponding integral curve. That means you have to solve a differential equations. And if you remember, I think for this kind of vector fields, your integral curve is I think if I if I remember correctly, this should be y square minus x square is some constant, that means it is again a hyperbola. Okay. But there is a, you will see, so this is the corresponding, it will give you the integral curves, and I have equipotential curves, but you will see that equipotential curves and the integral curves, they actually cuts orthogonally. Okay. So, for example, what is your integral curves? If you remember the integral curves, from the arrows you can guess it, right. So, then you will have this, or you will have this. So, this is the corresponding what is called integral curves, right. But what is this? This is actually your what is called equipotential curve, and integral curve is this one. So, therefore, maybe I think next slide, let me see whether I have written it not. Okay, yeah. So, that's exactly I have done it, look here. Okay. So, that is the heading. So, that means there is a kind of connections between the integral curves and equipotential curves, and answer is that integral curves and equipotential curves, they cuts orthogonally. What does it mean? Look here, I have written. So, integral curves and equipotential curves of a gradient vector field. That means, if I have a gradient vector field, you have the notions of equipotential curve, just now I have discussed, and also you know the notions of what is called integral curves. Now, if I go back, I think this I have already discussed what is integral curves, right. So, let me just have this example. Okay. So, this is conservative field, divergence of path. Yeah, look. So, integral curve. So, you know this is the definition of integral curve, and how do you calculate it? Look. So, I have discussed it. So, look. So, this is the corresponding vector field, that means x y flips to y comma x. Okay. So, I have to solve these differential equations. Now, that means corresponding, this is the vector field, in arrows you can visualize it, and of course, you see the corresponding integral curves, these are the integral curves. This is the integral curves. Okay, these are the integral curves, and what is the corresponding equipotential curve? So, this is like this one, this one. Now, you can guess what I am trying to say. So, this is the integral curve, right. So, that means this is equipotential, and this is integral, right, integral. Now, if they cut it at this point, but this orthogonal. Why? Because you just draw a tangent here and draw a tangent here, tangent here. Now, what is the angle? Pi by 2. So, that is exactly I have written there. Okay. So, that is exactly I have written. So, integral curves and equipotential curves of a gradient vector field. So, what I said, so at every point where your image of the vector field at the point f p is non-zero, then the integral curves through p must be normal or orthogonal to the equipotential curve or surfaces through p. Okay. So, that is exactly the statement. So, therefore, if I have a vector field, if I take a point p in the domain, of course, for the integral curve, you know that the image of the point capital P under the action of capital F should be non-zero. Then I have the integral curve passing through the point P, and at the same time I have the notions of equipotential curves, because it is a gradient vector field. So, I have the corresponding scalar potential, and you get the level curve or level surfaces. So, you will have the notions of what is called equipotential curve or surfaces through the point P. So, now I have two curves, one is integral curves passing through the point, another I have equipotential curves, and they say that there must be normal. So, this should be normal or orthogonal. Normal orthogonal means what? If they cut at a point, take the tangent corresponding to the integral curve and corresponding to the equipotential curves, and the corresponding angle between these two tangent at that point, it should be pi by 2. Okay, that is exactly the case. So, for a gradient vector field capital F, the integral curves and the equipotential curves form two orthogonal families of curves. So, that is the relations. Okay. So, one example it will be clear. So, okay, as I have written, as two equipotential curves, okay, that is another observations. As two equipotential curves come close together, that is very nearby, the magnitude of the vector field must increase. So, that is the observation. So, if I have two equipotential curves, they come close together, then the magnitude of the vector field actually increase. Okay. So, this is the corresponding example I have given. So, this is the vector field. What is my vector field? F of x comma y, which is exactly equal to y comma x, right. So, this is the arrows, you can have it. Now, the corresponding I have two things, one is the integral curve, another is the equipotential curve. Now, this is the integral curve, right. These are all integral curves, right, integral. This is also integral curve. And what is the equipotential curve? Just now I have discussed, look at the other one. So, this is the equipotential curve, right. So, what is this? And this is the equipotential curve, dot dot 1. So, this is the equipotential. Similarly, dot dot 1 is the equipotential curve. So, now look, any equipotential, suppose I am taking this is the equipotential curve, right, this is the one, and this is the corresponding what? Integral curve. So, two curve, they cut it at this point, right, and they cut it orthogonally. Why? As I said, you just draw a tangent here and draw a tangent there, and this is the angle pi by 2, this is the angle pi by 2. Okay. So, similarly here also if I take this equipotential curve, this integral curve, again draw a tangent here, draw a tangent there. So, this is pi by 2. So, that means the integral curve and equipotential curve they cut orthogonally, that is exactly I have written. So, must be normal or orthogonal. Okay. So, this is one of the example. Okay. So, I think that is the way. Now, I can visualize my vector fields in 3 ways. First one is that in terms of arrows. So, this is the one. Second one is that in terms of what is called integral curve. So, that means this is the one, not the dotted one, but the what is called line one. This is the integral curves. And in terms of dotted one, I can have the visualization of my vector field as an integral curve. So, 3 ways you can visualize your vector field. Okay. So, I think that is all about informations about vector fields. So, I have defined the what is the notions of vector field, and then couple of examples, and then I talked about what is the notions of what is called conservative vector field. Then there is a concept called path independence, then there is a concept called gradient vector field, and then these things are equivalent for a gradient vector field. And then of course, I have 3 ways I can visualize my vector field. One is the in terms of arrows, in terms of integral curves, and in terms of equipotential curves. And at the end I discuss that integral curves given a gradient vector field, corresponding integral curves and equipotential curves they cut orthogonally. So, now I am in a position to talk about what is the divergence, the notions of divergence and curl. Okay. So, this is the definitions. What is the divergence of a vector field? So, you start with a vector field capital F from some domain D subset of Rn to Rn, then capital F has n many components. So, I am just writing as small f1, small f2 up to small fn. Then first definition is that divergence of f, which I denote it as div of f, which is defined as what? So, sum of n partial derivatives, that means del f1 del x1 plus del f1 del x2 dot 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 del fn del xn. This is the corresponding divergence. So, that means what we will have? So, you have the corresponding del operator, that means del x1 del x2 up to del xn. So, that means del x1 del x2 up to del xn. This is the operator dot f, that means small f1 small f2 up to small fn. If I take the dot product, then what will happen? This will be sum, right. So, therefore, this would be del f1 del x1 plus del f2 del x2 up to del fn del xn, and which is nothing but this one. Okay. So, divergence of a given vector field, which is nothing but your del dot f, which is nothing but this object, del f1 del x1 plus del f2 del x2 up to del fn del xn. So, now of course, when I talked about the divergence, it is a scalar quantity, right, because I am considering the partial derivative at some point and then I am adding it, of course, because f1 f2 fn, what are those? These are scalar field, right, because f1 is a map from some subset D of Rn to R. Similarly, fi. So, each small fi is a scalar field. So, therefore, if I take the partial derivative at the some point, it will give a scalar, right. So, if I add it, it will be a scalar. So, therefore, divergence of f is a scalar quantity. So, for example, one example I have given, if I take this vector field f is equal to x square y comma z comma x comma y comma z. So, that means this is my vector field f of x comma y comma z, or is equal to x square y z x y z. It is a map from R3 to R3, right. And what is my small f1, small f2, small f3? So, my small f1 of x comma y comma z is x square y, f2 of x comma y comma z is equal to z, and f3 of x comma y comma z is equal to x times y times z. Okay. So, then you just use the definitions, you just calculate the partial derivative of f1 with respect to x, and then calculate the partial derivative of f2 with respect to y, and then calculate the partial derivative of f3 with respect to z. If I do that, then first one will give you 2xy, second one will give you 0, because I am talking about the partial derivative with respect to y variable, right, but this is a function of z. So, therefore, this is 0. And what about the partial derivative of the f3? f3 means xyz. So, that means z will not be there. So, therefore, you have xy. So, therefore, you have a 2xy plus xy, that means 3 times xy. So, divergence of f is equal to 3xy. So, that means divergence of f at the point x comma y comma z is 3xy. Okay. So, this is the notion of divergence of a vector field. Always remember that divergence of a vector field is a scalar quantity. Okay. Fine. Couple of properties of divergence. Okay. So, if I have two vector fields capital F and capital G, and if I have two real constant, and if I start with a scalar field, suppose f from Rn to R, then actually divergence behave like linear operator. So, that means divergence of A times capital A plus B times capital G, which is A will come out. So, divergence of A plus B times divergence of G. So, in other words, as I said, divergence is actually act as a linear operator. Okay. And if I take the divergence of capital A vector field times scalar field, okay, if I have this one, then actually it somehow, well, I should not say it behaves like Leibniz rule, but anyway, this is the formula. Divergence of small f, that means the scalar field times capital F, that is vector field. So, this is the formula they satisfies, that means first is that scalar field f times divergence of f, and then you take the gradient of f, okay, this is another vector field, right, gradient of f, dot product with the vector field capital F. Okay. So, that is the divergence of product of what is called scalar field times vector field. Okay. These are the properties, you can even verify, you just use the formula, like you just use the formula of divergence of f. So, that means del dot f, and that you just have this instead of capital F, you just replace small f times capital F. So, that means it will be there small f times capital F, and use the formula, I think you will be able to get this is the one. Okay. Okay. So, you just verify it, the corresponding formula, you just verify it, take it as an exercise and verify. So, you just use the definitions of divergence, you will be able to do that. Okay. Some interpretations of divergence, okay, what is that? So, divergence has to do with how a vector field changes its magnitude in the neighborhood of a point. Okay. So, divergence has a interpretations. First interpretation is that divergence has to do with how a vector field changes its magnitude in the neighborhood of a point. So, that means if I take a neighborhood around that point, how the magnitude of the vector field changes, divergence will tell you that fact, number 1. Number 2, the divergence measures the tendency of the vector field to diverge from a point. So, that is another interpretations. So, the divergence measures the tendency of the vector field to diverge from a point. So, number 3, if capital F represent velocity field, like in the physical applications, if capital F represents velocity field of a fluid, okay. So, suppose this is the corresponding vector field, that means velocity field of a fluid, that is the vector field capital F, then divergence of capital F represents the rate of expansions or rate of mass flow per unit volume of the fluid. Okay. So, therefore, if I take the velocity field of a fluid, that is the vector field if I consider, then if I calculate the divergence of my this vector field capital F, it represents the rate of expansions or rate of mass flow per unit volume of the fluid. Okay, this is one. Next one is that a point x, y, z. So, this is another kind of things, you can write it. So, you can note it down. A point x comma y comma z is a source if the corresponding divergence of my vector field capital F at the point x comma y comma z is positive. So, therefore, which means that there is a positive mass flow from the point x comma y comma z. So, the definitions. So, if I have a take x comma y comma z, you calculate the divergence of capital F at the point x comma y comma z. If it is strictly positive, because it is scalar quantity, right? If it is strictly positive, which means that there is a positive mass flow from the point x y z. Okay. Similarly, if I have a point x y z, it is a sink. So, first one is the source, second one is the sink. If the divergence of capital F at the point x comma y comma z, which is negative, which means that there is a negative mass flow to the point x y z. Okay. So, therefore, if I have a like vector field capital F, and if I have a point x y z, if I calculate the divergence of capital F at the point x y z, and if it turns out that it is a positive quantity, then I am saying that the point x y z is a source. In other words, I am saying that there is a positive mass flow from this point x y z. Okay. So, therefore, you start with the vector field, fix a point x y z, calculate the divergence of capital F at the point x y z. If it positive, then I will say that that point x comma y comma z is a source point. In other words, it means that there is a positive mass flow from the point x comma y comma z. Similarly, if I start with the vector field capital F, fix a point x y z, if I calculate the divergence of capital F at the point x comma y comma z, and if it turns out to be negative, then I will say that the point x y z is a sink. So, first one is the source, second one is the sink. In other words, it says that there is a negative mass flow to the point x comma y comma z. Okay. And if the divergence at the point x comma y comma z is equal to 0, then that point is neither source nor sink. Okay. So, this is another one. So, these are the interpretations of my divergence. Okay. Okay, one exercise I have given. So, for example, if I consider this what is called vector field, so I said okay, determine which points are source and which points are sinks. So, okay, that is kind of straightforward, you can do that. Okay. So, vector field is given, your corresponding small f1, small f2, small f3, this component are also given. Small f1 means this is small f1, this is small f2, and this is small f3, right. So, that means V is f1, f2, f3, and what is my f1? So, f1 of xy comma x comma y comma z, which is exactly equal to x q y z square, f2 of x comma y comma z, which is x square y square z square, and f3 of x comma y comma z is x square y z cube. So, now you have f1, f2, f3, right. You just calculate the divergence, okay, and check at which point the divergence is positive, at which point divergence is negative. Okay. Depending on that, you can say that which point x, y, z is source and which points x, y, z are sinks. Okay. I said that, okay, determine which points are sources and which, okay, that is the thing. So, you have to just check it. Okay. So, okay, I have written the answer. You say that, okay, if you just calculate it, I have not done it yet. Okay, when full calculations, you just calculate it. And you will observe that if y is positive, x is non-zero and z is non-zero, that means if x component and z component, if these are non-zero, depending on the sign of y, the points, so I have written, that means the points on the right of the xz plane. Okay. So, I do not have any condition on x and z, it is just non-zero point, but I am putting some condition on the y coordinate, that means it is positive, that means points on the right of the xz plane, then the corresponding point x, y, z is a source, and again, so x is non-zero, y is z is non-zero, that means I am not kind of disturbing the point x and z. But now, if the second component y is negative, that means points on the left of xz plane, okay, then this is a sink. Okay, so this is very straightforward. You just calculate the corresponding divergence and you just see that at which point it is positive and which point is negative. So, then it will have this kind of observation. So, that means if y is positive, x is non-zero, z is non-zero, that means points on the right of the xz plane, these are all the source point, and the points on the left of the xz plane, that means y is negative, but x is non-zero and z is non-zero, this is a sink point. Okay. One example I have given, I think physical example, which is that the streamlines of the vector field, again I have the vector field capital F x y is equal to map goes to x comma y goes to x comma y. So, what is that? The streamlines of this vector field are straight lines directed away from the origin. Okay. So, for example, for fluid flow, this means, what is the meaning of this one? It says that this means that fluid is expanding as it moves out from the origin. So, divergence of capital F should be positive, and if you just calculate the divergence, it is 2 positive. So, therefore, it is actually expanding, that is what it says. Okay. So, for this vector field, divergence if is positive. So, in other words, in terms of fluid flow, if I say for fluid flow, this means that fluid is expanding, okay, is expanding as it moves out from the origin. So, therefore, once it moves out from the origin, it is actually expanding. So, that means the divergence is positive. In fact, if you calculate the divergence, it is exactly equal to 2, and which is strictly positive. Okay. So, that means if you go away from the origin, it is actually expanding fluids. Okay. So, that is another physical example. Okay. So, there is another kind of field that is called solenoidal field. Okay. Solenoidal field. So, that is a definition. What is that? Okay. So, now I know if I have a vector field, then corresponding divergence I have said, right. So, there is a concept called what is called solenoidal field. What is the definition? So, I am saying that a vector field F in R3 is called the solenoidal field if the corresponding divergence of F is 0. Okay. So, that means this is a vector field. If I calculate the divergence, if it is 0, then I will say that this is solenoidal field. So, another I have written. So, a solenoidal field is also known as incompressible vector field or divergence free. You can see the divergence free because divergence is 0. Okay. So, that is another kind of way people can say. So, that a solenoidal field is also known as incompressible vector field or the divergence free vector field, that means the divergence is 0. So, for example, if I take this rotational vector fields capital F x comma y, which is nothing but minus y comma x, you just calculate the divergence, it is 0 actually. In fact, you can calculate it, right. Okay, that is very simple. So, let us do that. So, what is capital F? Capital F x y, which is minus y comma x. So, that means I can write it as f1 f2, right. So, what is my f1? f1 of x comma y, which is minus y, and f2 of x comma y, which is what? X, right. So, therefore, if I calculate del f1 del x at the point x comma y, what is this? So, this is if I have to take the derivative with respect to x, right. So, that means this is 0, and del f2 del y if I calculate at the point x y, again it is 0 because it is a function of x. So, therefore, the divergence, so therefore, divergence of f, which is nothing but del f1 del x plus del f2 del y, which is exactly equal to 0, right. So, therefore, the corresponding vector field F is solenoidal. Okay. So, therefore, like if I have a vector field, if you just calculate the divergence, if the divergence is 0, that means I can say that this vector field is divergence free vector field or incompressible vector field or solenoidal vector field. Okay. Okay. So, if divergence, okay, I have written the note, if divergence of capital F is 0, then the vector field capital F is neither expanding nor contractions or not contracting, I should say. Well, it is clear, right. So, because if I have a vector field, I already said that if divergence is positive, that means it is a source, and if divergence of F is negative at some point is a sink, that means they are expanding or contracting, right. Now, if divergence of F is 0, I mean it is expected the corresponding vector field is neither expanding nor contractions or not contracting. Okay. I have given another example. So, g of x comma y comma z. So, it is very kind of simple vector field. F1 component is 0, F3 component is 0, F2 component is x, but you just take the corresponding F1 with respect to x variable, this is 0. Now, if I take the partial derivative of F2 with respect to y variable, that is 0 because it is a function of x, and this is also 0. So, therefore, if I add it, so therefore, divergence of this g is 0, and therefore, g is solenoidal. Okay. So, this is kind of solenoidal field, that means if I have a vector field, if the divergence is 0, that is called solenoidal field. Sometimes it is called divergence free vector field or incompressible vector field. One of the example is the rotation vector field is like that. Okay. So, now I should next my point is to talk about curl. Before that, I need to discuss what is the cross product of two vectors in R3. I think if people are familiar with this kind of concepts in vector analysis. So, if I have two vectors in R3, what is the corresponding cross product, and I can write that cross product in terms of the determinants, right. So, this is the picture. So, if I have a vector A, if I have a vector B, this is my vector V, then what is my A cross B? So, that means you have a vector, you have a B vector in a plane. A cross B is actually perpendicular to the plane. Okay. So, that is the first one. So, suppose that is why in the picture is there, this is my A vector, this is my B vector, and this is the corresponding angle theta. Okay. So, A cross B, what is this? This is nothing but the vector which is perpendicular to the plane containing the vector A and B. So, this is the vector A cross B. Okay. So, that exactly I have written. So, the cross product of two vectors A and B R3 is defined as A cross B, and what is this? That is, you can write in terms of the determinant. That means, the first row should be I cap, j cap and k cap, that means the corresponding unit vector, and you have the vector A. So, A will have a this has a component A, say A1, A2, A3, and this will have a component B like B1, B2, B3. And then A cross B is a vector, and what vector you will have? This is the vector you will have. And what is this? If you remember, I think the calculation, right? What is it? This is I cap times A2 B3 minus A3 B2. This is the first one. Okay. So, then what will happen? Then determinant I have to do, therefore, plus j cap with a minus sign, I think. So, you can write it minus j cap. So, that means A1 B3 minus B1 A3. This is the one, okay, plus k cap. So, that means this is, so therefore, you have A1 B2 minus A2 B1. Okay. So, first one is I cap A2 B3 minus A3 B2, then minus j cap A1 B3 minus B1 A3, and then k cap times A1 B2 minus A2 B1. So, this is the vector is nothing but the A cross B. So, that means, if I know A, if I know B, I know A cross B, which is nothing but the vector parallel to the plane, okay, containing my vector A and B. Okay. So, okay, I have written actually. Okay. So, the cross product of vectors A and B in R3 defined as this vector, which I have written, is the unique vector satisfying this following. What is that? As I said, the A cross B should be perpendicular to my vector A cross B should perpendicular to the vector B, that means in fact it is the plane containing A and B, it is perpendicular. Norm of A cross B, this is a vector, that means I can talk about norm, it satisfies these properties, norm A times norm B times sine of theta, or theta running between from 0 to pi, and is the angle between A and B. So, this is the angle, right. So, if theta is the angle between A and B, I can have the norm of A cross B, that means the cross product in terms of norm of A and norm of B, which is nothing but this one, norm of A times norm of B times sine of theta, where theta is the angle measures in the anticlockwise direction from the vector A to B. If I have two vectors A1, A2, A3, B1, B2, B3, then I have A cross B, I am writing as C1, C2, C3, then this determinant condition satisfied. So, that means, if I put A1, A2, A3 in the first column, B1, B2, B3 in the second column, and C1, C2, C3 in the third column, and if I calculate the determinant, it is a positive quantity. So, these are the properties of the cross products. Okay, so in fact, this is a definition. So, definition means what? If I know A cross B, that means it satisfies this one. Okay. So, therefore, cross product of two vectors, of course, you are familiar with that, again I have just recalled it. Okay. So, first of all, cross product of two vectors is perpendicular to A, perpendicular to B. I can have the norm of A cross B in terms of norm A, norm B times sine of theta, or theta is the angle measured anticlockwise from the vector A to the vector B. And if I have, say, A vector is A1, A2, A3, B vector is B1, B2, B3, and if I write A cross B as C1, C2, C3, then the corresponding determinant is a positive quantity. And that is how you have the corresponding vector A cross B. If I know A is small a1, small a2, small a3 the component, if I know my vector B which is B1, B2, B3, then using the determinant formula you can have the vector A cross B. Okay. So, now once I have the notions of cross product, then I can talk about what is the notions of curl of a vector field. So, this is I have written curl of a vector field. What is that? You start with a vector field, again I am in 3 dimension. Suppose you have a vector field capital F from some domain D subset of R3 to R3. So, what is that? So, suppose capital F at the point x comma y comma z, which has 3 components like capital M, capital N, and capital P. So, this is first, this is second, and this is third. Okay. Then the curl of my vector field capital F, which I denote it as curl of F, and it is defined as curl of F, which is, if you remember, that divergence is the operator del dot F, but this time I am having the cross product. Okay. So, because del is del x1, del x2 up to del xn, or in this case what will happen, del x, del y, del z, right. So, this one in this case what will happen, this is del x, del y, and del z, right. And what will be your F? F is like in this case you have M comma N comma P. Now, I have this cross this, you know the cross product formula, right. So, what is this? The first row is I comma j comma k, second one is del x, del y, del z, that is the second row. And what about the third one? Third one is capital M, capital N, and capital P. And you just take the cross product. So, that means what is this? This will give a vector. What is the meaning? So, that means I cap. So, that means it should be del y of P, that means del P del y minus del N del Z. So, then first you do that side, then that side, do the calculation and then hit it with I cap. So, then what about J cap? Again it will have a minus sign, minus J cap times del x of P, that means del P del x, minus del Z of capital M, that means del M del Z, and finally you have K cap. K cap means you remove this rows and this column. So, what we will have del x of N, that means del N del x, minus del y of M and del M del y. So, that means curl of F, which is actually a vector quantity, whereas divergence of F is a scalar quantity. Okay. So, this is the notions of curl of a vector field. That means, if I have a vector field F, capital F, whose component is like capital M, capital N, and capital P, then curl of F, it is nothing but the del cross F, which is nothing but this one, determinant of this one, and if I expand it, which is nothing but, so first component of the vector along with I cap is del P del y minus del N del Z, minus j cap times del P del x minus del M del Z, plus k cap times del N del x minus del M del y. So, this is the first component, this is the second component, this is the third component. This is a curl of F. Okay. Let me see what I have written. Okay, some properties of curl. Okay, so what I've done. So, let F and G, I have 2 vector fields in R3. Suppose you have 2 real constant. Suppose I am starting with a scalar field small f. Then the curl of the vector field A F, A capital F plus B capital G. Again, it behaves like a linear operator, right. So, A will come out. You have curl of F plus B times curl of G. Okay. So, that's again, that means curl is acting as a linear operator. Not only that, if I have a, like in the divergence case, if I have a scalar field small f and if I have a vector field capital F, then I can calculate the curl of the product small f times capital F. Again, it is like small f will come out, then you have the curl of capital F, and then this time what we will have, gradient of f cross product with the scalar field vector field capital F. Okay. So, this is the properties of curl. So, like in the divergence, but this formula will have the differences. There we will have f times divergence, then this is a dot product, but here I will have a cross product. Okay. So, this is the properties of curl. Okay, so some interpretations of curl I have written. What is that? So curl has to do with how its direction changes. So that's the interpretations of curl. So curl has to do with how its direction changes. First one, then curl of a vector field represents what is called rotational motion. So that is important. So if I have a vector field and if I calculate the curl, it represents actually the rotational motions. Okay. Another one is that the curl measures the tendency. Look, that is very important. The curl measures the tendency of the vector field to curl around of a given point in a directions given by the right hand rule. Okay. So that is one actually. So that means if I have a thumb like that, and I have to have this kind of things. Okay. So that's exactly the things. So the curl measures the tendency of the vector field to curl around a given point in a directions given by the right hand rule. In fact, I have written, okay. So what does it mean? More precisely, curl is simply the circulations per unit area, circulation density or rate of rotations, amount of twisting at a single point. That's I tried to figure kind of given a picture to talk about that. For example, look at this one actually. Okay, so that means this is the kind of what is called curl around the given point it is given. So look at, so I have written, so this is the directions actually, kind of rotations it's giving. Okay, so I have written if the paddle does not run, it means this field has a curl at that point, and if it does not turn, then there is no curl. So that means there is a curl, means there should be a turn, there should be a rotation. That is the meaning of this interpretations of curl. Okay, so I think maybe next class onwards I will talk on that. In fact, there is a, once I have the notions of curl, then there is a notions of what is called irrotational vector field. Maybe that kind of concept I will talk about in my next lecture. So, but at least if I have a curl, so that means the corresponding vector field, if I have a curl, so that means the notions of curl of a vector field represents actually rotational motions. That means curl is 0 means what? That means there is no rotations. And curl, there is a curl, positive curl means that means there is a rotational motion is there. That's exactly I have written. So curl of a vector field represents rotational motions, and curl has to do with how its direction. Rotation means what? I am changing my directions. That means if I rotate it by the angle say pi by 2 or say pi by 3 or pi by 4, that means, so that means there is a direction changes if curl changes. If there is a curl, so it indicates how its direction changes. Okay. So I think I should stop here. So in my next lecture, I will, since I know the notions of curl and divergence, so there is a notions of irrotational vector field and couple of applications maybe I will talk about, and I hope within one lecture I will be able to finish those concepts. That's all I think for at least today's lecture. Next lecture, based on the definition of curl, I will talk about irrotational vector field and couple of more what is called examples and related kind of informations. I think I should stop here. Thank you.